What you are about to see is an exercise in imagination. We've been studying a crashed alien flying saucer. Here inside our top-secret hangar, we've examined the advanced technology it's built around. Now we'll go inside to discover what options are included on this model. An antimatter reactor, a teletransporter, laser weapons. With the help of leading physicists, astronomers, and engineers, we'll learn about its power plant, its weaponry, and most importantly, its mission. And maybe in the process, we'll learn something about ourselves through alien engineering. This is an alien spacecraft that crashed in the desert some years ago. We recovered it. Now our goal is to figure out how it works. We've been studying it for some time. Now we'll go on a remote video tour inside the craft. Our robotic camera is providing a remote video feed from the spacecraft housed at Hangar 18. As you can see, this is quite an enterprise. This is your first peek inside this alien vessel. Clearly, this is the main gallery, but it's not safe for humans to go inside just yet. We believe this is the sick bay. This is the facility. Every ship's got to have one, you know. Here are the control panels. This is where they operate the ship. We've hacked into their computer system, and we've learned a lot. Also, no joystick. We think they control it telekinetically. Below deck is the antimatter reactor. Now that's a complex piece of machinery, rather difficult to explain in lay terms. Camera off. So that's what's inside an alien ship, an antimatter reactor that can produce short bursts of intense energy to power exotic machinery like wormhole generators and warp drives. And it runs on antimatter, the highest octane fuel in the universe.
If you had 1 ounce of antimatter and you could annihilate it with 1 ounce of ordinary matter, that would give you an amount of energy equivalent to 1 million tons of rocket fuel.
Antimatter sounds like science fiction, but it's real. And we humans are making it right here on Earth. Actually, below Earth. At a government lab outside Chicago, 30 feet below ground, is a giant enclosed ring 4 miles in circumference. Here at Fermilab, the building blocks of the universe are being transformed into something fantastic.
Fermilab's mission is to do high-energy physics research. And high-energy physics research is trying to understand the forces of nature at the smallest distance scales. To see and investigate small distance scales, you have to have very high energy.
Why? Because the subatomic particles have to go fast, very fast. Fermilab operates one of the world's highest energy particle accelerators, called the Tevatron. Here, scientists make particles of antimatter.
Back in 1928, Paul Dirac determined that we have matter, like protons, neutrons, electrons, and the things that they make up, and particles which have the same behavior, but their charge is opposite. And the term that was come up with was antimatter.
Protons have antimatter counterparts called antiprotons, identical in mass, but opposite in charge. Electrons have anti-electrons called positrons. Antiparticles can combine to create anti-elements such as antihydrogen. Theoretically, any element can have an anti-element counterpart.
In 1932, Carl Anderson was the first person to detect the existence of anti-electrons or positrons from cosmic rays. And then many years later, in 1955, Emilio Segre and his collaborators at the Lawrence Berkeley Laboratory in California created the first beam of antiprotons by using a beam of protons striking a copper target, and they detected for the first time antiprotons. Those were the first proofs of the existence of antimatter.
Quantum physics predicted the existence of antimatter, but until 1955, scientists couldn't make any. It seems the universe is filled with matter and very little antimatter. So the most reliable way for us to have antimatter is to make it. That's what Fermilab does.
We create antiprotons by taking energetic protons and slamming them into a metal target. It creates enough energy density in the target that you can create particles, and there's a certain probability that you will create antiprotons. It's a very small probability, but it is large enough that we can actually create numbers that we can count. For every 500,000 protons that we put on the target, we can collect one antiproton.
This all takes place in the giant accelerator rings underground. They need all that room to get the particles moving fast enough before they hit the target to make antiprotons. After the antiprotons have been produced and collected, the stream of antiparticles must be kept close to the center of the tube and prevented from coming in contact with the walls.
We actually magnetically levitate it. We have a ring of electromagnets with a stainless steel tube which has all of the air evacuated out of it. That's about 500 meters in circumference. And these antiprotons that are collected after these collisions with this target disk are put into this ring which we call the accumulator. And this tube is big enough and there's no air in it so that the particles can just sit there circulating.
They have to keep those antiparticles isolated because if they come in contact with the particles in the wall, they will annihilate each other. So it would pose a big problem for beings like us who are made of matter if there was more antimatter in the universe.
It's a good thing that there's not equal amounts of matter and antimatter in the universe, because if I was to sit here in this chair and my antimatter counterpart came up and touched me on the shoulder, that would be the end of us and a good fraction of where we're sitting.
Matter and antimatter combine in a virtually perfect conversion of matter to energy. In other words, 100% of the matter and the antimatter become energy. Even in the best fusion reaction, perhaps 2% of matter becomes energy.
Antimatter is really the perfect form of energy storage because you get all of the energy out of the matter and the antimatter if you can make them annihilate. And that's a tremendous amount of energy. But a tremendous amount of energy is exactly what we need if we're going to power an interstellar spacecraft.
So what about using that tremendous potential for fuel?
Suppose you had 1 pennyweight of antimatter. That's 1/10 of an ounce of antimatter. The amount of energy in that 1 penny worth of antimatter would be enough to launch the space shuttle 60 times.
So what's the miles per gallon conversion on something like that?
If you had antimatter gasoline, you'd be able to travel 40 billion miles per gallon, and that's not even fixing your car up.
Great mileage, except that our nearest star neighbor after the Sun is in the Alpha Centauri star system 4 light years away. That's roughly 500 gallons, or 30 tanks full, to travel to Alpha Centauri. We humans will have to crank up the antimatter assembly line if we want to take a trip like that. Although Fermilab has been making antimatter for over 30 years, they've barely got any.
Fermilab has 1/1,000,000th of a gram of antimatter stored in its accelerators. With the rate at which we make it, it would take us about 40-some million years to make 1/4 of a gram of antimatter.
That means it would take billions and billions of years for us humans to make enough antimatter fuel to get to Alpha Centauri, unless we learn how to make it faster. Or we could just steal the alien antimatter supply and their engine. The aliens who designed the ship we found have solved many dangers and drawbacks associated with antimatter fuel. First, they solved the problem of antimatter storage tanks. Our alien ship has a miniature version of Fermilab's magnetic accumulator. The aliens also solved the problem of fuel supply. Either they have found a source for it out in space, or they can create it on a large scale because they've got a huge supply of antimatter on board. But as we solve one riddle, we encounter another. This alien spaceship clearly has turrets for weapons. What are those for? Defensive or offensive? What do our alien engineers intend to do to us? Weapons of mass destruction appear to be a standard feature of our alien spaceship. That's disturbing, but not really surprising. We'd like to assume any alien visitors would be friendly, or at least not belligerent when they touch down on Earth. But the aliens who built this ship clearly would rather be safe than sorry. How else to explain these death ray laser beams built into the ship? Come to think of it, it makes perfect sense to pack heat when you're penetrating space. You'll never know what you'll run into. Maybe you'll encounter hostile creatures along the way. Like us. We're fairly hostile, and we have our own Earth-grown futuristic weaponry. Naturally, they involve laser beams too. And we don't need alien technology. The U.S. military is working on several directed energy weapons.
A laser is just a device that allows you to send out a very coherent beam of light. If you think of a laser pointer that's used commonly now for briefings and stuff like that, it just allows you to get a very intense beam of light that goes a very long distance in a very small area.
In fact, the term laser is an acronym for light amplification by the stimulated emission of radiation. Focusing a laser is so simple, it's child's play, literally.
If you recall when you were a kid, you probably had a magnifying glass, and you used to use the sun to put a beam of light on a leaf or maybe even a bug, and you could create a lot of heat. That's what you basically do with the laser. You focus that beam of light on something that you'd like to damage or destroy, and you hold it in place long enough to heat it up and damage it or destroy it.
Lasers make excellent weapons for two reasons. One, laser beams travel at the speed of light, since that's what lasers are, light. Two, they can be aimed and focused with incredible precision. Not a lot of collateral damage with a laser beam. The first laser was actually a maser developed in the mid-1950s. It didn't use visible light, but instead harnessed microwaves and ammonia gas to create a beam. But by the late 1950s, optical lasers were created, and today they're everywhere.
Lasers are used in CD players, they're in dental drills, you use lasers in measuring devices. Lasers are everywhere pretty much.
Lasers can differ by wavelength or power. Less than a watt of electricity powers most commercial lasers. Military lasers are stronger. At the Laser Effects Facility at Kirtland Air Force Base in New Mexico, they can be much stronger.